In this new set of lectures, we are going to discuss the principle of virtual work. The principle of virtual work has been a very successful tool for many applications in structural mechanics. And perhaps the first application that you're used to from different structural analysis courses is the use of the principle of virtual work to find, so these are the applications, the use of the principle of virtual work to find displacements at specific points for linear elastic beam structures. For linear elastic beam structures. Now, the other application that is not that is very successful is that the principle of virtual work is the basis behind the new techniques, the new numerical techniques to find solutions to the equilibrium equations. So, is the basis behind numerical techniques, especially FEA, or in particular the FEA, finite element analysis in particular. And the purpose of these numerical techniques is to find approximate solutions to the equilibrium equations. So in this set of lectures we're going to talk about the principle of virtual work applies to a one-dimensional degree of freedom system of one-dimensional degree of freedom of 1D or 1 degree of freedom, and continuum systems and finally we're going to apply it to beam systems. Okay, so for 1 degree of freedom, the principle of virtual work states the following, or is derived as follows. First, let's look at a system, 1 degree of freedom system, made out of a spring and a weight mg. Now, at equilibrium, we know that the force in the spring, F, is equal to the external force, which is mg. So this is mg, and the force in the spring is acting opposite to the force, to the mg force, and at equilibrium the spring is stretched with the deformation delta such that F is equal to mg. Now this equation is equivalent to saying that for every a, which is a real number, it really doesn't matter, because if I apply F multiplied by A and I take mg and I multiply it by A, the equation doesn't really change, because for every A belong to R, this is true. F of A is equal to mg by A, which is basically saying for every real number, F minus mg A is equal to 0. But really it doesn't matter what A I put here, because F minus mg is 0. F minus mg multiplied by A is always equal to 0. Now I'm going to add some physics to this quantity, and instead of calling it A, I'm going to call it U star. What is U star? I'm going to just say that U star is a displacement. I'm going to just assume that it's a displacement. And so for any displacement U star, F multiplied by U star is equal to mg multiplied by U star And because this applies for any displacement, that means, of course, this is equivalent to saying F is equal to mg. And so what this when I call this u star as displacement, I can call F multiplied by u star as the internal virtual work in the spring. Work because it's equal to a force multiplied by a displacement. And mg multiplied by u star, I'm going to call it the external virtual work. External virtual work because it's the force, the external force mg, multiplied by the displacement u star. And it's internal virtual work because it's equal to the force in the spring multiplied by the distance u star. And so we arrive at the statement of virtual work that states that the internal virtual work is equal to the external virtual work in a 1D system. Now, how does this apply to a 3D system? In a 3-dimensional system, a continuum object, I have an object in equilibrium. Again, you have to say we're starting from in equilibrium. The object is in equilibrium, therefore there is a stress inside that object, a stress field, and on the boundary we have stresses acting on the boundary. The stresses are equal to the traction vector, which is equal to the sigma transpose n. And inside I also have the external force that's equal to rho b, the body forces. Now from this equilibrium, I'm going to apply a virtual displacement field. I'm going to call this virtual displacement field u star, and u star could be anything I want. And starting from the equilibrium equations, the equilibrium equations state the following: partial sigma 1 1 by partial x1 plus partial sigma 2 1 by partial x2 plus partial sigma 3 1 by partial x3 plus rho b1 is equal to 0. That's the first equation. And I have another equation, and I have another third equation. Now, similar to what I did in the first in a 1 degree freedom system, I'm going to also multiply here by any number. I'm going to call this number u1 star. Now, it really doesn't matter what u1 star is, because since this is 0, I can put here any number. This is true for every real number. I'm also going to multiply here, and this is true for every number. And I'm also going to multiply here by u3, and again, this is true for any real number u3. And then I'm going to spend one lecture worth of mathematical manipulations, which are not the subjects of the course here, to arrive at the following. That the internal virtual work in the continuum is equal to the external virtual work of the continuum. Now, what is the internal virtual work? The internal virtual work is equal to the integral of sigma 1 1 multiplied by the strain associated with this virtual displacement, plus sigma 2 2 epsilon star 2 2 plus sigma 3 3 epsilon star 3 3 plus sigma 1 2 epsilon star 1 2 plus sigma 2 1 epsilon star 2 1, and so on, integrated over the volume. This is the internal virtual work. The stresses in the continuum multiplied the stresses in the continuum multiplied by the virtual strains associated with the virtual displacement U star. The external virtual work is equal to the external forces multiplied by the virtual displacement. What are the external forces? Looking at the continuum, the external forces are the traction on the boundary and the body forces acting on the object. So the traction on the boundary is Tn dot U star integrated over the boundary plus the body forces vector, the dot product between the body forces and the virtual displacement dot integrated over the volume. So, and since internal virtual work is equal to external virtual work for any U star, any displacement field I put, this is equivalent to saying sum of forces equals 0, because the starting point was that the sum of forces or the equilibrium equations are equal to 0. So let's just utilize an illustrative example just to show what all the terms in the equations mean. I have internal virtual work, external virtual work, on the boundary, the forces on the boundary, the body forces, and all that. So let's look at an illustrative example to show what all these things mean. So I have a plate. Thickness of the plate is T equal to T. The dimensions are 2 multiplied by 1. It has 4 boundaries: boundary A, boundary B, boundary C, and boundary D. And the stress at every point inside that plate is equal to this matrix: x2, 5, 0, 5, x1, 0, 3 zeros, and the stress is function of the position. x1 and x2 are the coordinates of the position inside the plate with units in meter. And this is in kPa or kilonewton per meter squared. First, we need to verify that this stress is in equilibrium with a 0 body force vector, and we need to find the traction vectors or the traction forces on the boundary edges A, B, C, and D of the plate. And then we need to verify the principle of virtual work in the following 2 cases. If I apply a virtual horizontal displacement equal to this, and a virtual vertical displacement is this. So that's this is going to be a long problem. The solution will be long, but we will utilize everything that we studied from the beginning of the course. So the first thing we're going to do is verify that this stress is in equilibrium with a 0 body forces vector. So which means that if I have the stress, I don't have any internal, I don't have any body forces or any object that's pulling that plate. So I don't have any gravity field that's pulling the plate. Rho b is equal to 0. I need to show that rho b is equal to 0. To show that rho b is equal to 0, I'm going to substitute in the equilibrium equations partial sigma 1 by partial x1 plus partial sigma 2 1 by partial x2 plus partial sigma 3 1 by partial x3 plus rho b1. I know this has to be 0 for this to be in equilibrium. Partial sigma 1 by partial x1. Sigma 1 is equal to x2, so partial sigma 1 by partial x1 is 0. Partial sigma 2 by partial x2 is 0, and this is 0 plus rho b1 is equal to 0. And similarly, if you do this for the rest of the components, you find that rho b2 is 0 and rho b3 is equal to 0. Okay, so this is done. We verified that this stress is in equilibrium with a 0 body forces vector. The next step is find the traction forces on the boundary edges. So I know the stresses inside the object, I know that if this is the plate, I know that the stress at every point inside is equal to x2, 5, x1, 0, 0. Now, I have this is a state of plane stress. This is E1 and E2. Everything out of plane is 0, so I can just simply look at these. And imagine that this is everything is happening in that plane. So the stress is equal to x2, 5, x1. And now what I'm interested in is the traction vectors on the boundary. What are the forces on this on the boundary 1, boundary A, boundary B, boundary C, boundary D. Now remember, the traction vector on any boundary is equal to the stress matrix multiplied by the normal vector on this boundary. So let's find the normal vectors on each boundary. I'm going to call this NA. The normal vector on this boundary is equal to 1, 0, 0. The normal vector on this boundary is equal to 0, 1, 0. The normal vector on this boundary is equal to negative 1, 0, 0. And the normal vector on this boundary is equal to 0, negative 1, 0. So these are the normal vectors act on each surface. Now, I would like to find T and A, T and D, and T and B, and T and C. I know that the traction vector on any surface is equal to the transpose of the stress matrix multiplied by the normal vector. So this is equal to x2, 5, x1, and NA is equal to 1, 0. I'm only utilizing the in plane. Everything is happening in that plane. So this is equal to x2, 5. T and B is equal to sigma transpose NB, x2, 5, x1, 0, 1, which is equal to 5, x1. Traction vector NC is equal to sigma transpose NC, which is equal to x2, 5, x1, negative 1, 0. This is equal to negative x2, negative 5. The traction vector NT is equal to sigma transpose the normal vector on the boundary D, x2, 5, x1, 0, negative 1. So this is equal to negative 5, negative x1. So what does all these numbers mean? I'm going to draw the stresses acting on the boundaries. Remember, this is E1, this is E2, this is the dimension x, and this is x2. So on the boundary A, this is the boundary A, this is the boundary B, this is the boundary C, and this is the boundary D. On the boundary A, the stress is equal to x2, 5. x2 is horizontal, this is the horizontal component, 5 is the vertical component, which means that the stress acting on this boundary looks like this, 5, and the horizontal component is equal to x2. What is the value of x2 on this boundary? Let's see. On this boundary, x2 at this point is equal to 0. x2 at this point is equal to half. x2 at this point is equal to 1. So the distribution of the stress on this boundary looks like this. This is x2, and the value here is equal to 1. Okay, now what about the surface B? The surface B, the horizontal is equal to 5, and the vertical is equal to x1. So what's the horizontal? So the horizontal stress is equal to 5. So I have shear stress on this boundary that's equal to 5. And the vertical is equal to x1. Now x1 here is equal to 0. x1 here is equal to 1. x1 here is equal to 2. So it's a distribution that looks like this. And here the value is equal to 2, and the value here is equal to 0, and this is equal to x1. On C, the stress is equal to negative x2, negative 5, so this is the horizontal, this is the vertical, so the vertical is equal to negative 5, so it's in this direction, and a value of negative 5, and negative x2. So when x2 is 0, it's 0. When x2 is 1, it's equal to negative 1. So it looks like this. And then I'm going to put here negative 1. And this is x2. And finally, on D, the horizontal is equal to negative 5. And the vertical is equal to negative x1. So negative 5. So it's the arrows are pointing on the opposite direction. And I'm just going to keep negative 5 so that I remember to put the negative when I utilize this in the equations. And in the vertical one, you have negative x1. So when x1 is 0, it's equal to 0. When x1 is equal to 2, it's equal to 2, or negative 2. And so this is the stress distribution acting on the plate, or on the boundaries of the plate. And inside the plate, I have rho b is equal to 0. The forces, so these are the external forces acting on the object. Okay, so let's go back and read what we wanted to do for this problem. First, we verified that the stress is in equilibrium with the zero body forces vector, and we found the traction forces, or the traction vectors, on the boundary edges A, B, C, and D. The next is we want to verify the principle of virtual work. We want to verify that the internal virtual work is equal to the external virtual work. Now, to verify this, we need a virtual displacement u star. And the virtual displacement u star is given as a horizontal displacement u1 star is equal to ax1. So what does this mean? We're saying, assuming that the plate has a virtual displacement, it's equal to u star has two components, 0 in the vertical direction and ax1 in the horizontal direction. So assuming that the plate has a virtual displacement with arrows looking like this. So to verify that the internal virtual work is equal to the external virtual work, we first have to calculate this associated strain. Epsilon star is equal to half the gradient of u plus the gradient of u star plus the gradient of u star transpose. So we need to calculate the gradient of u star. The gradient of u star is equal to partial ui by partial xj, and this will be equal to a 0 and 0, 0. And so epsilon star will be equal to, after you take gradient of u star, add it to its transpose, and divide by 2, epsilon star will equal to this. So I only have epsilon star 1, 1 equal to a, everything else is equal to 0. And so that will make the internal virtual work easier to calculate, because the internal virtual work is equal to each stress component multiplied by the corresponding strain component integrated over the volume. Okay, so what is sigma on 1? Sigma on 1 is the stress in the current in equilibrium, the stress of equilibrium. The equilibrium stress, sigma on 1, is equal to x2. So x2 multiplied by a, integrated over the volume of the plate. What is the volume of the plate? Well, the plate has 3 dimensions, dx1, dx2, dx3. x1 changes from 0 to 2, x2 changes from 0 to 1, and x3 changes from 0 to the thickness of the plate. Performing the first integration, you'll get 0t, 0, 1, a multiplied by x2 multiplied by 2. Integrated now over dx2, dx3. Then, performing the second integration, I'm integrating x2, so this will be 0, 2, 2a, x2 squared over 2, integrate the values of at 0 and 1, dx3, which is equal to, again, from 0 to t, 2a, x squared, x2 squared is 1, so 1 over 2, integrated it over dx3. dx3 is from 0 to t, and so this will be a multiplied by t. And so the internal virtual work, which is equal to the stresses multiplied by the strains, is equal to a multiplied by t. Now Now, the external virtual work has many components. So we want to calculate the external virtual work. The external virtual work has the following components. Is equal to the external virtual work due to the external body forces plus the external virtual work on boundary A plus external virtual work forces on boundary B, external forces acting on boundary B, plus external virtual work forces acting on boundary C, plus external virtual work forces acting on boundary D. Now let's start with the external virtual work due to rho B. The external virtual work due to body forces is equal to the integral of rho B, which is 0 and 0, dot u star. Well, let's just write the equation first before we substitute. It's rho B dot u star integrated over the volume. This is the body forces vector is 0, 0, dot ax1, 0. The dot product of these two vectors is equal to 0. The integration of 0 is equal to 0. Now in your assignment, rho B is not equal to 0, so don't forget to include that term. Now the external virtual work acting on boundary edge A is equal to TNA dot U star on the boundary A, on the surface of the boundary A. So let's just look at the boundaries, analyze the displacements of the boundaries before we calculate the external virtual work on the different boundaries. This is boundary A, boundary B, boundary C, boundary D. This is x1, this is x2. U star is equal to the displacement is equal to A multiplied by x1. That's the horizontal component. It's equal to A, x1, and 0. So the virtual displacement on the boundary A, x1 on the boundary A is equal to 2. So this is equal to 2, 0. Because on the boundary here, x1 is constant at 2. The virtual displacement on the boundary B is equal to ax1. Sorry. This is A multiplied by 2, 0. So this is equal to the displacement, the virtual displacement on the boundary A is equal to 2a, 0. The virtual displacement on boundary B depends on x1. And x1 varies from 0 to 2, so this is equal to ax1. It really varies. If you're telling me if it's this point, it's going to be 0. If it's this point, it's going to be 2a. So I'm going to leave x1 without substitution. And u star d will be the same. ax1, 0. And u star c will be equal to 0, 0, because x1 on C is always equal to 0. boundary A is made out of, now we need to understand what's the domain of integration of each boundary. Boundary A, we have x2 varies and x3 varies. Let's maybe draw a 3D to understand the integration or the surface of each boundary. On boundary A, we're varying x2 and x3. So the integration will be done over x2 and over x3. In boundary B, the integration will be over x1 and over x3. The integration on boundary C, so this is A, B, the integration on boundary C will be over x3 and x2. And boundary D will be x2, will be x1 and x3. And so let's now do those integrations on each boundary. External virtual work on edge A or boundary A is equal to the traction vector on A. Traction vector on A, let's just go see what the traction vector on A looked like. x2, 5. Dot used star A is equal to 2A, 0. Integrated over dx2, this is edge A. Edge A has dx2 and dx3. dx2 varies from 0 to 1, x3 varies from 0 to t. The dot product between those two vectors is equal to 2A x2 integrated over x2 integrated over x3 from 0 to 1 from 0 to t, which when you integrate x2, this will be 2a x2 squared over 2. x2 will be 1, and then integrating over x3 will be equal to x3, and so substitute, you get t, so this is equal to a t. So this is the external virtual work on edge A. The external virtual work on edge B is the same. External virtual work on edge B will be the integration of the traction vector on edge B. The traction vector on edge B, let's go see what the forces on edge B is. It's 5x1. So this is the traction vector on edge B. T and B, which was equal to, so let's write it here, multiplied by the virtual displacement on edge B, integrated over dx1, this is edge B, dx1, dx3. dx1 varies from 0 to 2, and dx3 varies from 0 to the thickness of the plate. So this is equal to 0t, 0,2, and the traction vector on edge B was equal to 5 and x1. The dot product with u star on edge B, u star on edge B was equal to ax1, 0. When you perform this integration, this is the dot product, so 5ax1 integrated from 0 and from 0 to 2, 5ax1 plus x1 multiplied by 0, which is 0, so dx1 dx3. Doing the integration, this will be 5 over 2 a x1 squared, I'm going to substitute 4, so x1 squared is 2, 2 squared is 4, multiplied by the integration over x3 will be t, so this will be equal to 10, so 5 over 2 multiplied by 4, 10 at. The external virtual work on edge C is equal to T n C multiplied by the virtual displacement on edge C dx2 dx3, but the virtual displacement on edge C is 0. And finally, the external virtual work on edge D is equal to the integral of T and D dot, sorry, this is the dot product between two vectors, T and D dot U D star dx1 dx3, and so dx1 again is from 0 to 2, dx3 is from 0 to t. Let's go above, see what T and D is. T and D is equal to negative 5, negative x1. Negative 5, negative x1. Dot U star D is equal to ax1. dx1 dx3. Performing this integration, you get negative 5 ax1 squared over 2 integrated from 0 to t, and multiplied by x3 integrated from 0 to t, which when you substitute will be equal to negative 5 a multiplied by 2 multiplied by t, which is equal to negative 10 at. And let's now the external virtual work total is equal to external virtual work due to row B plus external virtual work edge A plus edge B plus edge C plus edge D, which will be equal to 0 plus AT plus 10 AT plus 0 minus 10 AT, which will be equal to AT. And indeed, the whole purpose is to show that indeed external virtual work is equal to the internal virtual work. And in doing so, you practice how to calculate the traction vectors, how to calculate the displacement on edges, how to do the integration on edges, and how to do the integration over the volume. Just a quick note, there's a difference between the external virtual work integrated over the edges and the external virtual work integrated over the volume. If the rho B was not equal to 0, the external virtual work of the body forces, if rho B was not equal to 0, the integration would be done over the whole volume, which is dx1, dx2, dx3, because the body forces are acting inside the object at every point. Now, in your book, this is performed again for a different displacement. So indeed, the external virtual work should be equal to the internal virtual work for any prescribed virtual displacement u star. And so in the book we've done this again for u star is equal to 0 b x2. And for this, the strain is equal to half the gradient of u star plus the gradient of u star transpose, which is equal to 0, 0, 0b. And in your assignment we have different forms for u star. You have to calculate the corresponding virtual strain. The same principle can be applied in beams, but starting with different equilibrium equations. Now the equilibrium equations for a continuum we've studied are equal to partial sigma 1 by partial x1. Let's just look at them. In a continuum, the equilibrium equations look like this. In a beam, the equilibrium equations have a different form. It's only one equation, which is EI d4y, where dx1 power 4 is equal to q. Again, if I multiply this by any u star or any y star, which is a real number, any real number, you get this. And after lots of mathematical manipulations, you end up with the principle of virtual work that states that if I integrate the internal virtual work made out of the moment multiplied by the second derivative of a virtual displacement y star, so I have a virtual displacement applied on the beam called y star, and if I integrate the moment from equilibrium multiplied by the second derivative of that virtual displacement and integrate it over the length of the beam, this is what we call the internal virtual work. The work done by the internal forces during the application of that virtual displacement will be equal to the external virtual work. Now, what is the external virtual work? Every external forces will be multiplied by the corresponding displacement. The first external force is the distributed load Q. Q will be multiplied by the y star. Now Q is at every point, so this will be integrated over the length. What else do I have? Well, I have the reactions on the outside of on the edges of the beam. I have V1, M1, V2, M2. V1 is upwards. This has to be multiplied by the corresponding virtual displacement y1 star. V2, but minus, because V2 is assumed downwards to be positive and y2 is assumed upwards positive. Plus M1 multiplied by theta 1, but because the positive moment is acting in this direction and the positive theta is always acting in this direction, so this is positive theta, so minus M1 theta 1. Plus M2 theta 2 star. And this is the equation of the principle of virtual work that states the internal virtual work is equal to the external virtual work. Now, when this applied to, let's do an example to show So in this example, we would like to apply the principle of virtual work for a beam just to illustrate that the internal virtual work is indeed equal to the external virtual work when a specified virtual work or virtual cubic displacement of this value is applied. So we have a simply supported Euler Bernoulli beam subjected to a distributed load that's equal to negative 5x1. Negative 5x1. Now we have for this E and I, Young's modulus, and the length is equal to L. Now we have a reaction here, I'm going to call it R1, and another reaction here, I'm going to call it R2, and another reaction here, R3, but I know that R3 is equal to 0. Now we need to verify that the principle of virtual work applies when I apply a virtual displacement, y star, is equal to a x1 squared x1 minus L. So the principle of virtual work states the following. The internal virtual work is equal to the external virtual work. I need to verify that this is true. So the internal virtual work is equal to the integration of the internal force, which is the moment, multiplied by the associated strain, which is the virtual strain, which is calculated based on the second derivative of the virtual displacement integrated over the length of the beam, while the external virtual work is equal to the work done by all the external forces. So the first one is negative 5x1 integrated over the length of the beam, so integrated multiplied by y star integrated over the length of the beam. So this is due to the distributed load, plus, now this is a concentrated force, multiplied by the corresponding displacement, so R1 multiplied by special y star, which is when x1 is equal to 0, plus R2 multiplied by a special y star when x2 is equal to L, plus R3 multiplied by 0, plus the moments multiplied by theta 1 star. Now that's plus m2 theta 2 star, where this is m1 and this is m2. Now m1 and m2 are equal to 0, so all this, in fact, you will find that this is 0, this will be 0 because m1 and m2 are 0, and you'll find that y star, when you substitute x1 to be L, then y star here will also be equal to 0, and when we substitute x1 is 0, you get that y star is 0, so this will go as well, and you're going to be left with this. And so the external virtual work, negative 5x1 multiplied by y star, which is ax1 squared, x1 minus L, integrated over the length of the beam, and this will be equal to a L power 5 over 4 when you perform this integration, you'll get AL power 5 over 4. Now what we are missing now is the internal virtual work. Now to find the internal virtual work, we need to find two things: the bending moment associated with the loading, and the second derivative of the virtual displacement. Now the second derivative of the virtual displacement is straightforward. The second derivative of y star with respect to x1 squared is, first perhaps we should calculate the first derivative and then differentiate. So the first derivative will be equal to 3a x1 squared minus 2al x1. The second derivative of y star with respect to x1 squared will be equal to 6a x1 minus 2al. And so now I'm just missing the moment, but to find the moment I have to actually solve the beam. So I have to find the bending moment of the beam. So to find the bending moment of the beam, I have to solve the differential equation of equilibrium. The differential equation of equilibrium I have this is the load EI, the fourth derivative of y with respect to x1 power 4 is equal to q, and q is equal to negative 5x1. Integrate 4 times, you'll find that EI y is equal to negative x1 power 5 divided by 24 plus c1 x1 cubed over 6 plus c2 x1 squared over 2 plus c3 x1 plus c0. 4 constants. To find those 4 constants, I need 4 boundary conditions. The boundary conditions are: the displacement is 0, the displacement is 0, the moment is 0, and the moment is 0. The boundary conditions are: at x1 equals 0, the moment is equal to 0. At x1 equals 0, the displacement is 0. And at x1 equal L, the moment is 0. At x1 equals 0, equal L, the displacement is 0. 4 equations to find the 4 constants C1, C2, C3, and you'll find that the displacement will be equal to C1, or negative 7 x1 L power 4 plus 10 L squared x1 cubed minus 3 x1 power 5 divided by 72, and the moment is the second derivative of this displacement. Differentiate once, differentiate twice, you get 5 over 6 x1 L minus x1 L plus x1. And now the internal virtual work will be equal to this moment multiplied by the second derivative. The moment multiplied by the second derivative of y star second derivative of y star with respect to dx1 squared integrated over dx1, and from 0 to L and the internal virtual work will be equal to AL power 5 divided by 4, which is also equal to the external virtual work above. And so I will also, in a different tutorial, I'll show you how to conduct all these integrations using Mathematica. So we're going to solve those two problems again using Mathematica, and you should practice conducting these equations, doing this by hand and using the software as well. Section 7.4.4 is not covered. And then in the next set of lectures, I'm going to talk about the applications of the virtual work. So we introduced the virtual work, the equations of the virtual work. We presented two illustrative examples where the external virtual work was shown to be equal to the internal virtual work for an arbitrary displacement, for just displacements y star or u star that we specified. And in the next set of lectures, we're going to show applications of the principle of virtual work.